Okay, let's get started. So we're going to start with Module 2 today. So we finished up Module 1 in the kind of the lab to get things preloaded. So we'll have intro to mag particle today, and we'll finish it up on Tuesday. But that way, when we go in the lab, I'm going to start walking you through some of the different methods, and you'll be able to have some of this background information now for remote visual inspection, and then magnetic particle inspection. So magnetic particle inspection, also known as MPI, is one of probably the most common methods used for small to medium-sized parts and for ferromagnetic parts. This one you have to have parts that are ferromagnetic. Anyone know what that means? What's ferromagnetic? Contains iron, right? So iron containing, which means they can be magnetized. Even some even stainless steel, for instance, contains iron. It won't hold magnetism, but you can perform, in some cases, you can perform MPI on it because you can magnetize it while you're performing the test. It won't remain magnetized afterwards, but you know, if it can be magnetized during the test, then you can use this. So before we do that, we're going to talk about, this is kind of a little side note, NDT, we've got three categories of what are called indications. So when you're out there, when you're performing NDT, you're going to need to classify your indications into one of three types. And so the first one is a real or relevant indication. Okay? And these are things that are true, a true flaw that you're detecting, something that's there. The second type is known as a non-relevant indication. And this is, we have, just by the nature of, the parts we're looking at and that kind of thing, is that there will be indications, there will be things that come up on your test or in your tests that are due to some feature of the part. And it could be things like geometry, it can be things like surface finish, it can be things like tooling marks that are there, when parts are made, if there's no reason to grind them perfectly smooth on a surface, they'll oftentimes leave the machining marks there because there's an added cost for cosmetic. And so if there's no need to remove cosmetic imperfections, they may be there, and they'll sometimes create a indication when you're performing NDT. But it's something that's expected, and it's not an indication of failure or of impending failure. The third one is a false indication, and a false indication is a mistake. Okay, this is an indication you get because of something wasn't done right, a process error. And it could be when you're doing penetrant type stuff, it could be that you didn't wash enough of the excess penetrant off. It could be that you overwashed it. It can be a fingerprint. You pick up a part while you're performing NDT on it and you leave fingerprints all over it. That's a false indication. Or you didn't clean the part properly and something on the part reacted with your chemicals or reacted with your test equipment. That's a false indication. So everything you do, whenever you're doing your reports and that kind of thing, you're going to need to identify different indications you get, and you're going to need to identify what type they are. Are they real, relevant? Are they non-relevant? Or are they false? And then even in some cases, a description of why, if it's one that's kind of on the edge, why do you say one or the other? And as part of when you have your practical exams, you'll need to be able to identify these three different categories as well. A lot of students kind of get, they seem to understand and know the real and relevant really well. The false and the non-relevant tend to kind of get a little bit of a gray area. So basically just know the non-relevant, some feature of the part causes it. And that could be, some features of the part causes it. A false is an error. In some cases, they can kind of go from one to the other. And what I mean by that is, like, if you have a part with small holes in it, when we're doing dye penetrant, for instance, those holes are going to trap the dye. A certain amount of trapped dye, a small amount of trapped dye, that would be a non-relevant indication. But if you didn't wash it enough, or if you left too much in, you didn't process it correctly, then it becomes a false indication. Okay, so you start to make those judgment calls about what it is. So when we're doing, all different types, we're going to do this. But to get back to, to get back to Mpi Particles, went too far. Again, we just talked about it real quick, but basic metallurgy, ferrous versus non-ferrous. The big key can be magnetized. Ferrous parts can be magnetized. So they're typically steel. They're steel, which is an alloy of primarily iron, and then things like carbon, and then a whole host of different alloying metals can go in there. You got silicone, tin, copper, nickel, anywhere from 8 to 20%. Versus non-ferrous are things that cannot be. So titanium, aluminum, brass, or bronze, which are copper and zinc, copper and tin. So magnetic particle can be done on these ferrous items. And then you can see I've got stainless steel there in the middle. It's primarily still iron, but it's got a lot of chromium in it, nickel, carbon, etc. And stainless steel, it can depend. Again, it will build up a magnetic field while you're processing it, and the way we do that is with electromagnetism, but it will not maintain that magnetic field after you shut the electromagnet off, after you shut the current off. So all metals, however, are electrically conductive, and that's the other thing is for magnetic particle, we have to be using electrically conductive, but ferromagnetic in its own right means it's going to be electrically conductive. However, if something's painted, it may not be very conductive. So these have to be bare metal objects. Little bit of basic metallurgy and things that are going to come into play, especially when you are looking at what kind of indications we've got. Parts we deal with on aircraft can be cast. We take a liquid metal and pour it into a mold. Okay, they might be forged. Forged is to basically pound metal into shape. They can be extruded. That's to send metal through a restricted opening. That's like the snake maker thing with Play-Doh, right? Pack the Play-Doh in, you push it down, the little snake comes out the end. That's extruding. Rolling is like a rolling pin or a big rolling mill, right? We flatten steel or other materials. And then finally, machining is then to cut material off or cut things away. And all of those can leave different types of finishes on the surface that can cause different types of indications. So for instance, castings and forgings in general create a fairly rough surface, just the raw casting, raw forging. And so that can trap dye, that can trap metal particles. That can be hard to get a good bond on when you're doing things like eddy current testing. Extrusions can leave lines and things down the length of a part. Rolling can leave feature, can kind of create surface, but it creates a smoother surface. And then machining can leave all kinds of different marks depending on how finely finished that surface is. It can also be very highly polished from machining as well. So you just got to kind of keep those in mind for knowing what's expected or not expected and what the limitations might be. So we need to select our technique, okay? And so as we go through this, kind of think about what you can use these different techniques for and what you can use this technique for. So things to know, technical capabilities. What do we have equipment for? What do we know how to do? What are our people certified for? What kind of an expected flaw are we looking for? Are we looking for something at the surface? Are we looking for something that's subsurface? Are we looking for something fairly large or fairly small? And so different things like that. How critical is it? Is it an area, can we have a less precise method that's maybe cheaper to do? Or do we need to reuse that really, really precise, very sensitive method because it's such a critical area? And it goes into the cost and the time side of it as well. As things become more precise, as they become more sensitive, they tend to go up in cost. They tend to take longer to do. They take more training and skill. Types and size of parts, you'll see when we go into our lab, our mag particle bench will only fit parts up to a certain size. They do make bigger benches, but if you don't have the bigger bench, you can't put a bigger part in the one we got. Our dye penetrant bench, the buckets are only so big. If you want to dye pen something bigger, you either have to paint the dye on or you got to get a bigger bucket. Environmental conditions, things like humidity, temperature, the lighting, how bright is the lighting? Is it the right type of lighting? Is it white light like we have in here in the classroom? or are we under black light where we can see things that glow, that fluoresce? And then the type of material. You don't want to use a liquid-based inspection on a porous material that's going to absorb a bunch of it, right? You can't use dye penetrant on a lot of composites because the fibers are going to wick up the dye and you have no way of getting it back out. You have no way of cleaning it. It could actually chemically damage it. So all those things go into effect when we're choosing our method. And so as we go through these, kind of think about what does this method lend itself to do? So mag particle inspection. Here is a picture of a part that's undergoing magnetic particle inspection. What do you think we're seeing here? Let's go indications. What do you see indication-wise? What's that? Think those are scratches? Think those are shear stress? Shear stress creating what? Those are cracks, okay? Those are cracks. Any other indications you see? So what kind of an indication are those cracks? With classifying, relevant, non-relevant, false. What kind of indication would those cracks be? Those are a relevant indication. Do you see anything else going on here? Any other indications where the dye, where it's glowing? What about the volt holes? They're glowing. Why are they glowing? Yeah. It's not actually because the volt's rubbing in that case. It's not reflection. Yeah, Quinn? Yeah, so it just collects. Those are areas where the fluid collects. Okay, you can't help that in this case. So those would be what kind of a those are non-relevant because it wasn't a mistake. There was a big fingerprint in the middle of it. That'd probably be false. Anyone see any other? What about the fact that the whole surface is glowing? What's causing that? Okay, this is mag particles. So these are actually magnetic particles that are in a liquid. The surface finish, it's a rough finish. So it's going to trap a certain amount of that stuff. So is that relevant, non-relevant, or false? That's a non-relevant indication. Okay, so in this image, there really aren't any false. You've got non-relevant in terms of the particles collecting in the bolt holes. Because what's happening is these particles are attracted to magnetism. We magnetize the part, we put magnetic particles that have fluorescence on them. So those holes have a lot of magnetism. They're going to hold a lot of stuff in them. That rough surface, stuff's going to hook to it. We'll look at why it does that in a minute. And then the cracks that you can see are what's showing up. That's what we're looking for. Okay. You guys all recognize it's the end of a crankshaft where a propeller probably hit something. Okay, cause that shear or a torque. It's a twisting, a torsional shearing is what it's called. So MPI, all these methods, each method's going to have a list of advantages and disadvantages. So MPI, you saw these cracks under white light, if we just had this part out, would not be visible. You wouldn't be able to see these with the naked eye. So it's highly sensitive to small flaws. It's primarily used for surface cracks, but you can find some subsurface defects at certain times. It's a very quick method. When we do it, you'll see it really doesn't take that long to perform. The longest part of the whole thing is the inspection after you perform the method. So you perform the mag particle, you apply the magnetic particles, and then you have to inspect to see. That one's pretty obvious. Some things, the indications are much, much smaller than that. It requires moderate skill to perform. You'll all be, you're all going to do this. You're all going to be able to perform it, be able to demonstrate it by probably the second or third week in the semester. There are portable versions. Our version that we have here is not. It's a workbench, but there are versions that don't require a bench, so they can be semi-portable. And relatively speaking, it can be fairly inexpensive. Okay, you don't have to buy the bench. You can buy some little hand electromagnetic probes for a few $100 and some little magnetic powder, and you can do this for about $400 or $500. In the great scheme of things, that's pretty cheap compared to the $250,000 X-ray equipment. So However, there are disadvantages with everything. So again, I mentioned ferromagnetic parts. The parts have to be able to be magnetized, even if it's just temporarily. You have to be able to access the entire part. So this is typically done on parts that are removed from the aircraft or from the equipment they're installed in. You can't mag particle an entire engine. We had the crankshaft there. You can pull the crankshaft out. But you can't just take an engine and stick it in there. You'll end up with magnetic particles stuck everywhere inside the engine. Kind of a bad thing, right? The magnetizing part does have you're running current through it. You're going to run a high current, thousands of amps through a part. So there is a chance that you can overheat it or even weld it. Okay, if you don't put the parts into our bench tight enough, you'll get arcing and you'll actually damage the part. You'll damage the contact pads on the bench. So you got to make sure the part is in nice and tight so you got a good current path. When you're done, you have to demagnetize the part. You don't want to put magnetic parts back into an engine or on an aircraft. Why not? It's going to happen. There's two main concerns. So, what's that? It'll collect material. So engine parts, if you put a magnetic piece back in, like a crankshaft, every little metal shaving is going to stick to it. What's going to happen? No. Well, I mean, you'd have to have a lot, but well before it comes unbalanced, what do you think? What happens if all the metal shavings stick to the crankshaft or the connecting rods? Because what? Causes wear. Those parts will get into the journals and everything, right? That magnet. You want to get rid of any little metal shavings and whatnot. You want them to get caught in the filter, not get between the bearing journals and all that stuff. What about a part on an airplane? What do you think a magnetic part on an airplane might do? It throws off the avionics and navigation equipment. In fact, when an airplane gets hit by lightning, steel parts can be magnetized. We'll use a Gauss gauge to check the magnetism on the parts we're testing. But when we were working on aircraft that got hit by lightning, we'd have to go around with the same Gauss gauge and figure out if anything on the airplane got magnetized. And then if it did, we'd have to demagnetize it. The big culprits were landing gear. The landing gear legs are often made of steel. Those would get magnetized. The metal around the window frames would get magnetized, and you've got your whiskey compass on the flight deck, right? It's right by that windshield. So, stuff like that, we got to be careful. So we got to demagnetize everything, things out, the flux gates, the heading, the things that sense the Earth's magnetic field out in the wingtips. You'd have metal parts. You don't want anything near those. It would magnetize screws that were near those and throw those off. So you got to we have to demagnetize all our parts here. So you'll have to show that you demagnetized the part when you were done. You have to demonstrate it to me. You have to remove paint if you're dealing with painted parts. And then at the end of the day, even after you perform this method on there, it relies on you looking at the part and identifying the cracks. So your visual acuity and the human factor, human element comes into play. So ultimately it's visual detection. You have to see the cracks that are made visible by the magnetic particle inspection. So what's going on with ferromagnetic particles? Just a quick physics review is that particles or atoms in a material are going to be, they're polarized. They have a positive and a negative pole on them. In ferromagnetic materials, what we can do is align all those poles to create a part that has a much stronger magnetic field. And that's what's being shown here on the right. On the left, it's basically showing particles are every which way. When they're every which way, those little tiny atomic-sized magnetic fields all kind of balance each other out, and there's no magnetism. But if we take all the little atoms that make up a part and we flip them all so that their poles are aligned the same direction, that's what creates a big magnet in the rest of the part, the entire part. And so that's what it is. When a part is magnetized, it's had all those poles aligned. When we want to demagnetize it, we need to re-scramble them. And we'll show you how to re-scramble them. And the same process may need to be used on a plane that's had a lightning strike or something like that. That magnetism is known as flux, okay? The actual magnetic field is also known as magnetic flux. And so in our case for this, when we want to create it, we do that by running current through a part. right? A moving current creates a magnetic field. And so we run current through a part, it creates a magnetic field, it orients all those atoms, and that's going to have a certain orientation and direction, right? There's going to be a positive or negative end. When we're doing this, we don't care which end is which. You know, we don't care what the North Pole is or what the South Pole is. We don't care which end Santa lives on. We just want to magnetize it. We want to get them aligned. And then when we're done, we will demagnetize it, okay? But it's oriented, the big key, remember, is the flux, the magnetic field forms 90 degrees to the current flow. And we'll look at where that's important is we have to magnetize our parts in more than one direction to make sure that we can see cracks that go in more than one direction. Okay, if a magnetic field is parallel to a crack, we won't see it. And then the actual magnetism is greatest while the current's being applied. And then depending on the material, it may stay magnetized. That magnetic field may go away. In different materials, that is going to occur faster or slower. And so it's greatest while it's being applied. We want to inspect it just after that point. And we're going to check it before you do the inspection. You're going to magnetize the part. You're going to apply these particles, but then you're also going to need to check that it was magnetized properly. And we measure that those units of flux are called Gauss. And so we have a Gauss gauge, a Gauss meter we run by the part. And we check what the flux level is. And where this works, ultimately what happens is when a part is magnetized, you have this magnetic flux going through the part. If there is a discontinuity, a crack, that flux will have to jump from one side to the other. And when it does that, you have a little bit of field now exposed to the elements, so to speak. And that's where those little magnetic particles will stick. Okay, so that's what was happening here, is flux was jumping across each of those cracks and magnetic particles is sticking to it. And those magnetic particles are coated with a fluorescent coating. And so what we're seeing is where those particles are being caught by the magnetic field that's jumping across the crack. We'll look at that in a little more detail here. So just quick image of that. So here's the right-hand rule. You have your direction of current through a wire. You can see here we're running current through the wire. You get these circular flux rings that go around the part. Okay, so that's that 90-degree current, or sorry, 90-degree flux, 90-degree magnetic field to the current. Some properties we have to understand. So the first one is permeability. And that is different materials can be made magnetic easier or less easy than others. Okay, iron is very permeable. It's very easy to magnetize pure iron, right? Stainless steel is less permeable. It's not as easy to magnetize stainless steel. Plastic is not permeable at all. In theory, you can magnetize plastic if you had a way to run enough current through it, but you would destroy it before you ever got all those poles to line up. Okay, any material can theoretically become magnetized, but practicality's sake, it's not going to happen. Okay, so even some of those materials, even aluminum, you can generate a magnetic field on it while you're running current, but as soon as you remove the current, it's gonna, they just re-scramble themselves. Okay, so reluctance is the opposite of that. That's the resistance to magnetism. So iron has high permeability, it has low reluctance. Okay, aluminum has low permeability, high reluctance. Okay, it's reluctant to being magnetized. The flux density is how strong that magnetic field is. It's based on how tightly together those flux lines are. Residual magnetism is when we're using electromagnets. We send a current through a part, we send a current through something. It's magnetized while that current's running. When we shut it off, does it stay magnetized? Residual magnetism is the magnetism that sticks around. Okay? Iron has high residual magnetism. If you run current through iron, you shut the current off, that iron bar will stay magnetized to some extent. Okay. Aluminum has low residual magnetism. You run current through it, you get the poles aligned. As soon as you shut off current, they go back to being scrambled, and your residual there is no residual magnetism. Okay. Retentivity is the opposite of that. So the ability to hold the magnetism. So iron is highly retentive. Aluminum is not retentive. You see where these are? So permeability and reluctance are opposites. Residual magnetism, retentivity are opposites. And then finally, if we're trying to figure out how easy or hard it is to magnetize something, you have something called coercive force. Okay, and something that iron does not require a lot of force to magnetize it. Stainless steel requires more force, more coercive force to magnetize. You can magnetize stainless steel, but it's going to take more effort. It's going to take a higher current from the electromagnet. And so it requires more of that coercive force. That's, you can think about it, you're coercing all those atoms into aligning with each other. Okay, you're trying to coax them into alignment so that they become magnetic. With every material then, put those together, and we're going to get a magnetic properties diagram that forms something called a hysteresis loop. And so this kind of shows where some of these things or how some of these different things are happening. Okay, so we start with a material. What we've got here with this graph, across the x-axis is the magnetizing force. This is the electromagnetic, the electrical current we're running through. How high is that current, right? So 0, current can run two directions. It can run to the right, or it can go positive, it can go to the left. So our electric current is our x-axis, is our magnetizing force, right there. Okay. The y-axis on this is the flux density. That's how strong the magnetic field is at a given current. Okay. So our material, if a material is not magnetic, now some materials obviously can be magnetic when we go up to them, right? You have magnets that they have a high retentivity, they retain magnetism. But most materials are going to start out at the origin of this graph. They're going to start out at the 0, 0 point right here. And when we first turn on a current, they're going to follow that dashed line. Okay. And what'll happen is they'll follow the dashed line, and you can see the strength of the magnetic field goes up, and then it continues to go up, but slower and slower and slower till it reaches something called the saturation point. If I were to continue to turn up the magnetizing force, the current, after this material reaches its saturation point, it would continue to make a line straight to the right. Why? What does saturated be? It's as saturated as it can be. It can't become any more magnetic, can't become any more magnetized, because why? What's happened in that material? There's only so many atoms and electrons that can orient, and everything at that point is oriented. When we reach a saturated point, everything's oriented. So we want to use enough current on whatever it is that we're testing that we reach the saturation point, right, to get the strongest field possible. But we don't want to keep applying more and more current beyond there, because why? The part starts to heat up and you can potentially melt or arc it. Okay, and you're not going to get any more out of it. Once you've reached the saturation point, you got what you got. Okay. Now our bench, and most benches, most systems like this, use alternating current. They use AC. Okay. So then what starts to happen? We've reached the saturation point. Now the magnetizing force flips, right? The direction flips. So it's going to start to come back a little bit. And this is one cycle. Now, anyone know how often our cycles flip in the United States? You know what the frequency is of electricity here? It's 60 hertz. So this happens 60 times a second. So we're looking at 1/60th of a second right here. Okay. So as that magnetizing force flips, we're going to go back, and you can see when we get to zero, when the magnetizing force gets to zero, the magnetic field doesn't actually go to zero because of that property of retentivity. The part wants to hold on, you know, especially in this case, this is showing a diagram for typically an iron or a ferromagnetic part. If we were looking at aluminum, it would go almost all the way back to zero. But in a ferromagnetic part, the type of parts we're going to test, you can see when for that split second where the current goes to zero, it maintains a certain amount of magnetism. And in fact, it's retaining like almost 2/3, most of the magnetism, right? So at any given point, if we shut our machine off, it's probably going to maintain magnetism, right? It's nearly impossible to catch a point where there's no magnetism. So that's the retentivity. And then it takes a certain amount of force, certain amount of reverse electromagnetic force, reverse current, to bring it back down to zero magnetism. You can see it's this very short time from point B to C right here. Right? You see it's a very small amount of time right here. Or ramping up of the current, I should say. Okay. So it does pass through the 0 point again, and now your atoms are all starting to flip the opposite direction, right? And at some point, then what's going to happen? What do we reach? What's D down there? D is our other saturation point. This is now all the poles have flopped to the other direction. Okay. The what? No, right now it's magnetized. It has the same force in the opposite direction. When it's not magnetized is when it's right here at H, right in the middle. Okay, the poles flipped. Right? They talk about the Earth one day, the poles will flip, cause havoc. Maybe we're due for it to happen. Right? Ionosphere collapse. All life as we know it'll be wiped out. Right? So that's what's happening in the middle here. And then, sorry, don't mean to be all doom and gloom. We are overdue for the poles to flip, though. Okay, so now we've gotten them saturated in the opposite direction. Then what happens? Alternating current, 60 times a second. It goes back the other way, right? So we hit another, we have that coercive force again. It's going to want to stay somewhat magnetic, even when, for that split second that the current shuts off as it's reversing. It's going to take a certain amount of reverse current to scramble everything back around to bring magnetism for zero. And it's going to go through this point real quick. And then it's going to continue to come up to saturation on the positive side again. Okay, so it's going to keep doing that back and forth for the time that you do. So we hit our part with a little bit of electricity. And basically, when you let go, there's a button on the machine. When you let go of the button, it's going to end up at one of these retentivity points. Top one, bottom one. Okay. If we want to get a little bit more, we can actually hold the button for a second, apply the particles while we're holding the button, and then release it. So it's at saturation for the most part. And then it comes back down to retentivity, and that hangs on to any particles that it's caught in that split second it hits saturation. Okay. But you can see here, it'd be really hard to, to time the button press just right to get the magnetism to go away, right? So a little bit later on, we'll talk about how we can use this to demagnetize the part. This diagram is going to make a reappearance. It's going to make a reappearance in the lecture, and it's going to make a reappearance on your exams. Okay? So you need to know this hysteresis loop. Okay, now remember I said some of those magnetic properties are related, some of them are opposite. So here's just kind of a quick reference for how that works. So again, permeability If it's high, reluctance is low. If flux density is high, if residual magnetism is low, retentivity will be low, corrosive force will be low. So you can see iron doesn't take a lot to become magnetic. It likes to stay magnetic. Harder steels, as you get closer to the stainless steel, it doesn't like to be magnetized as much. It doesn't like to hold on to its magnetization, but it will magnetize to a certain extent. So how does the MPI work? Let's see some images. So here's our magnet. This is a permanent magnet instead of electromagnet. But a magnet like this is going to generate a field. And then when you have a metal part, iron or other ferromagnetic material, the flux is going to want to travel through the iron, right? That's going to transport the flux easiest through those atoms that are all lined up. But if we get a crack, you get what's called flux leakage. And that's where you can see this little bit of magnetic field jumping from one side of the crack to the other. Okay. There is also, what's not shown here is the portion of the magnetic field that jumps from end to end. So this is like a bar magnet. There is flux jumping from end to end like this. Okay. But that's not really what we're looking for. That's not really going to attract our particles. What's going to attract our particles are these little jumps right here at the crack. And so as it's jumping, we put some magnetic particles there, and you can see they get trapped in that little jump of magnetic flux. Something like that. Okay? And that's what becomes visible. Then we have these particles, ferromagnetic particles. They can be two types. They can be just dark colored or colors. You can get these little magnetic particles or iron particles, or basically iron filings, iron shavings. And they coat them in either colored materials for visible light, if you're going to look at them under white light. Okay, that's what the portable systems use, like a dry powder. Or the ones we'll be using are coated in a fluorescent dye or a fluorescent material. And so then you shine a black light on it and it glows. And you can see where more particles are being held on the part versus areas that have less where it doesn't glow as much. So that part we looked at initially, those cracks held a lot of those fluorescent particles. The rough surface held some, but there was an obvious contrast there between where the cracks were and where the cracks were not. So how do we actually make this work? It kind of wraps up theory. Now we're going to look at the process. So the Mpi process can be broken down into a few steps here. So the first thing we're going to do is clean the part. Then we're going to magnetize it. While we're magnetizing it, or once it's magnetic, we apply these ferromagnetic particles, these little iron filings that either have visible coatings on them or fluorescent coatings on them. Before we inspect it, we have to check that we have a good magnetic field. And then finally, we can do our inspection. Okay, that's to perform the process. There's two more steps that occur here after, four more steps that occur after this. Once we've done the inspection, we need to demagnetize the part. Again, we don't want to put magnetic parts back into an engine, back onto an airplane, because all they'll do is pick up every little chunk of metal or throw off navigation. And then after we demagnetize, we verify it's been demagnetized by checking for the magnetic field, making sure there is no residual magnetism. We then need to clean off any residue, any of our testing material, and then you're going to report out on the results. Okay. So first step, cleaning the part, we need to make sure that the particles have unimpeded access to the leakage field. This field does not jump very far from the surface. Okay, a thick coat of paint, it can be thick enough that it blocks this little flux jump from being able to pick up any particles. So that's why this can't be done on painted parts. This process has to, that's a second reason. The first reason is you don't get a good electrical contact. You can't run electricity through a painted part, like paint is a resistor. And you would probably, if you do manage to get it to go, you would burn the paint in the process. And then the second is that the paint can be thick enough that the magnetic field won't jump up the surface of the paint and catch anything. So it's also essential it's not covered with contaminants. So even things like oil and grease can be thick enough that the field can't jump. Or imagine if a part's covered in a bunch of grease and you dump iron filings on it. What's going to happen? They're going to what? Oh, huh? They're going to stick. Yeah, they'll get stuck everywhere. You know, they'll get stuck in the grease or the dirt. So those all have to be removed. And so you'll typically use cleaning materials such as solvents or detergents. So we've got the cleaning tanks that have the mineral spirits in them that you can use. I've got alcohol, isopropyl alcohol is another good one that dissolves oils and greases and that kind of thing. But then the part needs to be fully dried. Why is that? Huh? So it doesn't rust, could be part of it. It doesn't burst into flame. We're not servicing oxygen here. So what if I have a part covered in alcohol and then I go put it in the mag particle bench that's full of an oil-based carrier? You think those will react with each other? Alcohol breaks down oil, by the way. Right? So it's not going to react properly. Okay. So we want to make sure they're clean, they're dry, they don't have anything that. So don't let your cleaning materials become contaminants in their own right. Then we need to magnetize the part. And the direction of the magnetic field is important to detect cracks in all orientations. So the magnetic field is going to jump across a crack, but if the field is running parallel to the crack, it's not going to jump anywhere. Okay, so that's why we have to run in a couple directions. Circular, so what we use, we run the current through the part, that's known as longitudinal current flow. And then we have a coil on the bench. There's a coil we can put around the part to run current around, circular around the part, which is going to cause the magnetic field to run longitudinally, or the length of the part. Okay, so a longitudinal current running through the part from end to end will create a circular field around our part. A circular field around the part will create a field running longitudinally through the part itself. They're opposite. That 90-degree thing comes into play. The current required is specified by the part manufacturer. What you'll find is we've got a lot of engine parts. In the engine manuals, it states how much current is needed. When you're doing your own tests, you can kind of say, okay, I brought in this little doohickey and it's about the size of an engine valve. You would use a similar current. Or I've got this big head off of my 5.7 liter engine. You know, it's as big as a crankshaft. You're probably going to run a similar current, 2,000 amps, 2,500 amps through that sucker in order to get it to that saturation point. The actual current is established by trial and error. Different parts are going to conduct differently. So you put the part in the bench, you start with the current adjustment set low, and then you step it up until you get to the required current. It's not going to hurt anything to have a lower current run through it at a period of time. But if a part runs at 2,000 amps, you start low, okay, a couple of clicks, it's on 4, you're only getting about 1,000 amps, you turn it up to 7, you're getting about 2,000 amps, you turn it up to 9, you're getting 2,500 amps, it goes to 11. No, ours only goes till 10. There's no 11 on our machine. You can't read it. Everyone knows what I'm talking about? Spinal tap. You haven't seen it. It goes to 11. They got a special amplifier for their band. It goes to 11 instead of 10. Okay. And then we check that the part's magnetized to make sure that it's reached the saturation point. Okay. And we do that with a flux gauge. So here's what it looks like. You point the arrow towards the part. Now, a flux gauge only works if you're moving through a magnetic field. So you have your part here. You bring the flux gauge is about this big around, about the size, a couple inches in diameter. You have to be bringing it back and forth past your part, and you look for deflection of the needle. If you bring it up and set it next to your part, the needle's going to read 0. It has to be moving through the magnetic field to give you a reading. Okay, so you basically are waving it over the part and making sure you get needle deflection. Okay. we'll leave off there. The next section we get into looks at our test bench and how to actually use it and that kind of thing. But we are out of time for today.